All right. So let's get started with our new topic that we were looking at, which was mixture models, right? So mixture models is one type of a latent variable model, and we'll discuss more latent variable models later on. But today I'm going to start with one type. So as I said in the last class, right? So there is a general concept of latent variable models where you observe something, and we denote our observations with x. But what we assume is that this x is actually generated by some hidden variable z, right? And this z is not known, so we call that the latent variable, and we want to find what that z is, right? So that's the idea. So we are going to look at, and then based on what x and z are and what these probabilities are, there are many types of latent variable models. We'll see 2 or 3 of those in this class. So today we are going to focus on mixture models. All right, so let me introduce that. So technically, mixture model means this: the latent variable z can take one of k values. All right, which means that z is categorical, and we denote the probability distribution for z as a multinomial. So if you remember, multinomial is nothing but it gives a probability for every possibility, right? So for example, a roll of a dice is typically modeled as a multinomial distribution because it can take 6 values, right? Same way, a simpler form of multinomial is of course binomial or Bernoulli, in which z can take only 2 values, 1 or 2, or heads or tails, right? In that case, we only have a number pi, a scalar value between 0 and 1. So the way this mixture model works is that if we knew z, then for every possibility of z, there is some probability distribution for x, okay? And so it is written as this conditional distribution, of course. That is, the PDF of x depends on what z is, and sometimes, just to save a lot of writing, we denote it as pk of x, which is just a notational simplification of this thing, right? So if I know an x, right, if I see an x, the probability for x over all possibilities of k would be written as this, right? So let me write it here. Right. So what we are saying is that we have some x, right? So this is observed, and x belongs to some d-dimensional space, right? So it's a vector of d attributes, right? And then we have, so this is observed, and then we have z hidden, and z can take, let's say for now, we'll assume that z can only take 2 values, 1 or 2, or 0 and 1, right? And we are going to model z is modeled as a Bernoulli distribution, and later we can relax it and say if it takes k values, then it's modeled as a binomial distribution, which means the distribution, this parameter of this is pi, right, which is the probability of heads, okay? So we have 2 probability values here: probability of z equal to 1, that will be pi, and probability of z equal to 2 is equal to 1 minus pi, right? So that's just the binomial distribution or Bernoulli distribution. On the other hand, x, right, we don't have the direct distribution for x, okay? We don't know what p of x is going to be. What we have is, what is p of x going to be given z equal to 1 and probability of x given z equal to 2, all right? So just to keep it simple, we sometimes denote it as p1 of x and p2 of x. So these are the PDFs for x for these 2 different latent variables, all right? So if I want to find, so if I ask you what is p of x, right? P of x, which is just the, so this is kind of like the marginal of x, because we are marginalizing what z, the value of z would be. So this would be written as p of x given z equal to 1 times p z equal to 1 plus p of x z equal to 2 times p z equal to 2, right? Because you are essentially marginalizing the z with this, right? So if you remember, when we do when we were looking at probabilistic models, right? This used to be like the denominator, right? Whenever we said, okay, let's, I mean, there we used to use a y, but the idea was similar, right? So this is this. So this is p of x. And typically what we will say is that assume that the distribution has parameters. It has some parameters. We don't know what they are, but let us say we are denoting them with a theta, right? So sometimes we also write this quantity as p of x given theta. So for a given theta, this is going to be my probability of x, right? So in general, so let's say in general, if z can take k values, let's say z belongs to 1, 2 through k values, then we can write p of x given theta as essentially a summation, right? So okay, let me just go back to this two case. So now what is this, right? P of z equal to 1 is pi, right? And p of z equal to 2 is 1 minus pi, right? So you can write this as p of x given z equal to 1 pi plus p of x z equal to 2 1 minus pi, right? And remember that we are, just for simplification, we are going to denote it like this. So this can be written as p1x pi plus p2x 1 minus pi, right? This is just the terminology here. Now in general, if z can take more than 2 values, if it can take k values, then we can write this as p of 1x. Now instead of just having a pi, because pi as a scalar, where pi is a scalar, only works if this takes 2 values, right? But if z takes k values, then your pi will also be a vector, right? Basically it will have a vector with k elements, and each element will tell you what is the probability of that category, right? So that is how the multinodal distribution is specified. So then I can write this. So then p1 of p z equal to 1 will be pi 1, p z equal to 2 will be pi 2, and so on. So we can write this as p1 pi 1 plus p2 of x pi 2, and so on until pk, right? Or you can just write it as a sum, k equal to 1 through k, small k, pk or pi k, pk x given theta, or x. Sometimes we also write the theta here because theta are just the parameters of this distribution, all right? So this is the general form. So if I know all of these values, then I can compute the probability of x, all right? So you can think of these pi's as some kind of mixing probabilities, okay? So let me give you an example. And we'll come back to that later as well. Right. So, okay. So an example. Let's say these two. So each one of these k's are called mixture components. So think of it as a mixture of some distributions. All right. So each of these. So you have k distributions in a mixture, and then you see a z. Or then you observe an x. Now you don't know which mixture generated it, right? So the process works like this, right? So there's a box which contains k distributions, right, for mixture model, and then when you need an x, right, when you want an observation, what you say is you basically shake the box and say, give me an x. Now inside what happens is one of the distribution parameter, one of the distribution in the mixture will be chosen, okay, and that will be chosen using your pi, right? And then once that is chosen, then that will give you the value. So for example, let's say your mixture looks like this. Let's say you have two mixture components, and so k is equal to 2, right? And let's say each one of your mixture component is a Gaussian mixture model, right? So this is our box, right? And inside this, there are two Gaussian distributions, one which has a mean of mu1 and variance of sigma 1 square. And let's say these are one-dimensional Gaussians, and this mean of mu2 and sigma 2 square, all right? And then there is a number pi here, which helps us determine which one to choose, all right? So the way we sample from this mixture component is that first we shake the box. So shake the box means that it chooses one of these, right, based on this probability, right? So this is like a coin toss. Think of some tiny person inside who tosses a coin, which has a probability of heads as pi, and then it says, okay, it's a heads, so then it goes here. Okay. Then from here, it picks out a sample because this is a Gaussian distribution. So it picks out a sample from mu1 and sigma 1 square. The next time you need another sample, you again shake the box, you get the other value, and so on. All right. So let me give you I hope I have a quick demo here. Let's see. So let's say we are trying to sample 1000 data points, okay? And let's say our pi, I'm going to call this pi. I'm going to create another. Right. So let's say pi is 0.3. That means that when you shake the box, with 0.3 probability, it will pick the first one, and with 0.2, it will pick the other one, okay? And let's say mu1, which is the mean of the first distribution, is 0, and sigma 1 is 0.08, all right? And let's say mu2, which is the mean of the second distribution, is 0.6, and sigma 2 is 0.12, all right? So now what we will do is, instead of doing this, in a loop, what we will do is we'll say for I in range n, which means I'll do this loop 1000 times. Now every time I will first sample from this pi distribution. So I will say just Bernoulli, and I'm going to sample from Bernoulli. Sorry, pi dot what? How do you sample from Bernoulli? Completely forgot. Draw a sample. Oh yeah, here it is. Bernoulli.rvs theta. Right. So every time I will toss the coin, it will give me either 1 or sometimes it will give me 0. So it's 0 or 1. So let's consider 2 as our 0. All right. So once it will give 1, otherwise not. All right. So now if s equal to 1, which means I found the first, I chose the first distribution. Now I will sample from the first distribution. Okay. So I'll say v is a sample from, how do you sample from a Gaussian distribution, is here. Right. So norm here. Yes, so I will choose the first one, right? And then I'll choose 1. Okay. And else I will choose from the other one. Right, so every time it gives me this, and then what I'll do is I'll create a empty samples, and I'll keep appending it to samples. Right, samples. So what will happen now is this process will run 1,000 times. Every time it chooses one component of the mixture based on this probability, and then it does that, right? So now if I plot the histogram for this one, I just want to see what is the empirical distribution of this. Change it to an array on samples, right? You're right. Yeah. Okay, so this is how the empirical distribution looks like. So if you remember, the means of the two distributions were 0 and 0.6, and these were the sigmas, right? So what happens is that every time I select one of the distribution, I sample from that, right? So at the end of it, when I see all of my samples together, this is the empirical distribution of this. So the heights of these are governed by pi, right? Which means that on an average 0.3% of times or 30% of times, I chose the first distribution, and 70% of time I chose the second distribution, right? So if I change my pi, make it 0.5, that means that both of them are equally sampled, then the general volume would be the same. Now in this case, this looks thinner because its sigma is small, right? So otherwise they'll look exactly the same. In fact, if I make this like this, right? So it's generally the same, right? So that is the idea behind how the mixture model generation works, right? But that's not what we want. The useful part is that if we have this data, okay, can we estimate these means and sigmas and the pi, right? So that is what we are going to sort of understand today and on Wednesday, is that this is how the process worked, right? But if I only give you these points and don't give you the pi and the theta and everything, can you tell me what will be the pi, or what will be the two distributions? I mean, what will be the parameters for each one of these distributions, as well as what will be the pi? All right. So the general idea is that, of course, you can choose anything, right? I can say that this data was generated by a single distribution whose mean was 0.3 and variance was something, right? That would not be a very good guess, because if you compute the likelihood of this data set given that, it won't work very well. It won't come to a very high value. Similarly, I can say that this was generated by two Gaussians. One was centered at 0.4 with a variance of 0.1, and another was centered at 1 and a variance of 0.1, right? But that would not fit this data very well, right? So we want to find those means and those pi's which fit this data the best, and we'll come up with an algorithm to do that. All right, any questions so far? Okay, let's move on. So this is the question that, that this is how the x is, right? And we want to compute all the thetas and pi's. Now the theta in this case is all your means and sigmas, right? But remember that here I chose a Gaussian, both p's to be Gaussian, that given z equal to k, this is a Gaussian, but in general it could be something else as well. You can choose some other distribution. You can choose a gamma distribution or beta distribution. It's up to you, right? But today we are going to look at the case where we assume that p x z equal to k is a Gaussian, all right? Which means that this theta would contain k means and k sigmas, all right? And right, so that's why we will call these Gaussian mixture models. But in mixture model is a more general concept. It could be applied to some other type of distributions as well, right? So now how do you use it? Of course, if I knew these thetas, right, this becomes very useful because now I can use this to basically understand the distribution of x, right? So that is useful. You can also use it for clustering, right? So for example, remember here, if I knew all these thetas, I can compute this value, right? Px equal to k will be this much, right? Which means that I can apply the Bayes rule and compute the posterior. I can say what is Pz equal to k given x, which given this is my x, and given that these are my distributions, which which mixture component did it come from, right? So if I go back to this thing here, if I now give you, let's say I have already estimated my x's, right, my mu and sigma, okay? Now if I give you a new point, let me give you a point 0.8, okay? Then I can easily compute what is the probability of 0.8 to come from this mixture component and what is the probability to come from this mixture component, right? So in some sense, it gives you a notion of clustering. So if you think of this z are essentially indicators, right? So let us say you have k clusters, then you can compute what is the probability of each of your data point to come from each cluster. So it's kind of a soft clustering. The reason it is a soft clustering is because you are not assigning it to one data point. You can have non-zero probabilities for everything, right? So remember the last discussion that we had for clustering was that k-means clustering is what we call hard clustering, which means that it assigns every point to exactly one cluster, which means that z equal to k will be 1 for one of the k's and 0 for everybody else. But for using this Gaussian mixture model or mixture model, you can do what is called soft clustering, which means that you could get something like p is equal to 1 is 0.8, p is equal to 2 given x is 0.1, and so on. So it's not hard, all right? So you can use it for that as well. Any questions so far? All right, so now let us see how to learn these parameters, right? So I kind of showed this demo to you, right? Here we went in the generative way. We knew the parameters and we created the data. Now we want to go back. If we have the data, how do we learn the parameters? And that is what machine learning is, right? We always go from the training data and go back. So this is what is given to us, right? We have been given some data points, and right now I'm assuming that they are one-dimensional data points, which means they have only one value, but later we can generalize it to vectors as well. And we want to find the generative model, right? So we have done this for one mode, right? When we were looking at parameter estimation for Gaussians and other distributions, right? What we say in that case is we assume that our data is coming from a Gaussian, and then we do the MLE estimate or map estimate to get the parameters, right? This is easy, right? And it will work if your data is indeed coming from a Gaussian, from one Gaussian. But what happens if the data is coming from multiple Gaussians, right? So there is not one Gaussian, right? Which means that if I try to fit my model on this, a single variate model, it will not fit very well. So how do we get that value, right? So let me just see what else I had here. Right, so here it is. So let's first focus on this plot over here, right? Now here, this is the distribution of the data, which is empirical distribution. It's just a histogram, right? So it's a one-dimensional data point. Now it clearly shows that this is coming from a single Gaussian, right? So now what you can do is you can compute the MLE, right? So you remember MLE is just the sample mean and sample covariance, sample variance in this case, right? So in fact, here I'm just using a Python function called fit, which just takes this data and gives you the mean and variance, right? But you could have computed it as well by just taking the mean of this and the variance of this, right? And so what we see here is that this distribution, or this red line, is the PDF, actual PDF that we have learned. That PDF fits the data very well, right? But now let us focus on this second data set. In this data set, you can clearly see there are two modes, right? But if we force it to learn a single distribution, this is what it will learn. This will be the mean around here, and this will be the variance. Now you can clearly see that it doesn't fit very well, right? And we can also see that, oh, maybe this is a combination of two Gaussians. So how do we estimate the parameters of these Gaussians, right? And that is what we will look at now, all right? Excuse me. Sorry about that. All right. Okay. The problem with this type of, yes. Uh-huh. Right. Right. Yeah. So I mean, yeah, so that was visual, right? So the question is, how do we in general know if it fits the data well or not, right? So in two-dimensional, one-dimensional case, of course, you can see it like this. But in general, you want to find the fit, you want the likelihood to be large, right? So if the because you have, essentially this gives you some probability. Now these are all your data points, so you can compute the likelihood for this data set, and that needs to be large, all right? All right. Now the biggest problem here is that we don't know what the z's are, right? We don't know the latent variables. So that is why computing the mu1, sigma1, mu2, sigma2 is hard, right? If we knew z, which meant that if we knew which mode did the data point come from, then we could have easily computed it, right? So for example, if zi's were known, zi's are essentially those latent variables, right? That means your data looked like this. Let's say your data looked like this. 0.7 came from mixture component number 1, so this is zi, this is x, right? 0.6 came from 1, 0.8 came from 1, 0.3 came from 2, came from 2, 0.4 came from 2, 0.5 came from 2, 0.65 came from 1, right? So on. So let's say this is your data set, yeah? Now, estimating mu1, sigma1, mu2, sigma2, and pi is easy in this case, right? Because pi will be what? Pi will essentially be 1, 2, 3, 4. Actually, so pi will be 4 times 8, right? Which is the number of times you see zi equal to 1 in the whole data set, right? So that is easy. Mu1 will just be the mean of all those x's for which zi is 1. So mu1 will be the mean of all these values, and similarly sigma1 will be the variance of all of these values, right? And same way with mu2. Of all these values, right? However, in reality, we don't have these, right? All we have are the values. Now, how do we compute pi1s and mu1s, right? So that becomes the tricky part. So one way somebody could say is, how about we explore all possible assignments, right? So let us say, let's first find out the assignment in which all are ones, right? Of course, that's a degenerate case, but let's say in that case, we can set mu2 and sigma2 to anything, right? So we can compute for, we can explore all possible combinations of z. The z is just a vector, all of these z, right? And then for each value, we can compute these, right? And then we can compute the likelihood of this data set, right? So because you remember that given all these parameters, you can compute the probability for each data point, which is this, and then you can compute the log likelihood, right? So whichever gives you the best log likelihood, you can choose that as your solution, right? However, so we can all possible combinations z and compute the log likelihood choose the best, right? Or choose the assignment and mu and sigma for which the likelihood is the maximum, right? But that of course is computationally infeasible, right? Not feasible because there are 2 power n possibilities for z, right? Because z can take 2 values, there are n values, so there are 2 power n. So as soon as your n becomes larger than something, 50 or so, you are looking at a very large search space. So that clearly is not the right way to go, all right? So what is the right way to go? So one way to do it is that since we know the likelihood, right? So we can compute the likelihood, which is this. Right. So this is the probability of each data point, right? Now here there is no z because we have marginalized over all z's, right? Which means that now I can compute the likelihood, which is for all x's, right? And then I can maximize it. Yeah, that's our standard MLE procedure. Now, of course, as I said, if zi were known, that would have been an easy task. But if zi is not known, then you have to do that marginalization, right? Then what will happen is that that function will be harder to optimize. So let me show that to you, right? So this is what the function will look like. Well, it's over here, right? So this is the probability for each data point, right? And remember, the probability for each data point will be given as this, right? Because you are going to marginalize over all values. So let's try to write it nicely. So likelihood, or actually log likelihood of a mixture model, or actually log likelihood of D in a mixture model. Let's say your data set is D, right? So the probability of each point, let's say point number xi, given the theta, we had written this as probability of zk. So this was a summation, right? Summation k equal to 1 through k ck, and then probability of xi given this k, right? So you remember this part, right? Now if I want to compute the likelihood of this whole data set, then likelihood of the data set will just be product of all probabilities, right? This is I equal to 1 through n, right? And then if I want to compute the log likelihood, I just take a log of this quantity. So this product becomes a sum. So it looks like this: I equal to 1 through n log of p of x of I given theta, right? And then I can replace this here, log of, right? So this value is the whole thing here. So it is log of summation p of zk p of k xi given theta, right? And this goes from k equal to 1 through k, right? And sometimes we also write p of z of k as pi k. So this is a multinodal distribution, all right? So this is our log likelihood, right? So now, so I can just, let me write it like this. Pi k theta, right? So now this quantity does not have z in it, right? That means that to compute the log likelihood, we don't really need the z assignment because we have sort of marginalized over all possibilities of here, right? So in principle, we can maximize it, right? Because this is a log likelihood, we can maximize it to find the pi's and the thetas and get our answer. But the point is that this is a very hard function to optimize. The reason being, there is a summation inside the log. Whenever there's a summation inside a log, it becomes very hard to compute the derivative, right? Because if you think of any, let's do a little sidebar, let's say you have some log of x plus y, right? and this is our function, okay, as a function of x and y. So if I want to differentiate it with respect to x, right, of this becomes pretty hard. 1 over x plus y times this, right? Yeah. And so the point is that now setting this to 0 gives you all kinds of problems. Maybe for this very simple example, it's not that evident, but when you get to very large expressions, right, having a summation inside a log makes it very tricky to optimize. In fact, if you think about this function, right, this function will look very, it will have a lot of local minimas and everything. Okay, it will not be a smooth convex function to optimize, right? Which means that it is not easy to optimize over it. All right, question so far? So the point that I'm trying to make here is that for a mixture model, you can express the log likelihood as a function of your parameters, right? And it does not require to know what your z's are, right? However, maximizing this is not easy because there's a summation inside the log term. All right. So in fact, I want to give you, and then so next class we will look at an algorithm which does this without having to maximize it. But before that, I want to give you a small demo. So let's say, so I'm going to try to maximize it anyway. Okay. So let's say we have all these functions, and let's say this is my data. Okay. So I have generated some data which looks like this. It has clearly two modes, two mixture components, and we want to learn the probabilities that so these were the initial probabilities that I started with. So sorry, the model parameters, right? So for the component 1, the mean is 0 and the sigma is this. Component 2, mean is this, sigma is this, right? So I got the data. Now I want to find this data back, right? So what I can do is I can use our scipy.minimize, right? So I can write my log likelihood, which is a function, right? So here is the log likelihood function. It basically computes the log likelihood. It essentially does this, this quantity inside here, right? So this is the internal core function. So I give it one x, and theta essentially contains all of your parameters, the mu1, sigma 1, mu2, sigma 2, and the pi. And then you compute that pi times p of z1, p1 of x, and 1 minus pi times p2 of x, right? So this is the, and then I do it for all of my data points, and then I compute the log, so that gives me the log likelihood, right? And then I try to, and I put a minus sign here because I want to minimize it, right? Actually, we want to maximize this quantity, so I put a minus and then use a minimize routine. Now, one thing you will note when you have done your assignment is that this is basically your NN obj val or your obj val whenever you compute it. But in your case, you not only had to compute the objective function, but also the gradient, right? In this case, computing the gradient is tricky. So what I will do is I will let the minimize routine approximate the gradient. So sometimes, you have a function, you want to minimize or maximize it. Sometimes it's hard to compute the gradient. So then what happens is many of these functions, what they do is they numerically estimate the gradient. So gradient is nothing but, you find the value of x of fx at x, you find its value at x plus some delta, and then you look at the tangent and the slope, right? So that gives you the numeric gradient. So that's what I'm going to ask it to do. So I give it the obj val, which is this. I give it some initial parameters, initial settings, and then I say just run it. I pass it the data, right? And then this is the function that I'm using. And what happens if you run this is that it is not able to converge. The reason being that that function, right, it becomes very tricky to optimize. Okay, there are many other methods. So you've been using conjugate gradient descent, but there are others as well. So there is Powell. You do that also fails to converge, gives all kinds of warnings. So maximum number of function evaluations have been exceeded because it is very hard to optimize. I use this one, which is Nelder-Mead. Nelder-Mead seems to do pretty well. In fact, if you see, right, so it is pretty close to 0.07, which is 0.8, 0.08, 0.6, 0.12, and this was my pi, which was 0.3. So Nelder-Mead in this example was able to find it. But in general, if you have a lot of data, you have many mixture components, even Nelder-Mead might not work very well. There was another function which is a version of that BFGS, which also kind of does okay, not too bad, right? So that is fine. But in general, what happens is that because of the complexity of the function, right, it is very hard to optimize it using direct minimization, right? So now let us see how to do it in a different way. So there is another algorithm called expectation maximization, right? This is one of the very famous machine learning algorithms, which lets you optimize this function without explicitly doing the gradient descent kind of routine. All right. So next time we will see how to do that. But the general idea is this. All right. General idea is this. So let's say this is your function. Okay. This is what you are trying to maximize. You're trying to find this point. So you're trying to find the theta at which you reach here. Right. This is a illustration. In general, we are assuming that theta is one value and then a scalar value, and then L is a function of theta, right? Now, if you apply a general gradient descent, it might not be able to optimize very well because it has all kinds of funny business going on here. So what expectation maximization does is that it says that instead of directly trying to optimize it, they come up with another function, Q, okay? So what they do is they, at any point in your iterations, you find this another function which is convex at that point, and then you try to maximize on that, and that is easy, right? Because this is a purely convex function, so you can reach this point. Now when you reach this point, now you jump up because you know this point, and then you again find another convex function there, and then you jump up, and so on. So that is sort of the basic principle behind expectation maximization, and it is based on a very interesting principle that I don't know if you're familiar with, but something called a Jensen's inequality, right? What a Jensen's inequality says is, this probably is I mean, just for your knowledge, but this is not going to be covered in the exam, right? So what a Jensen inequality says is that if you have a function f of x, right, and let's say x is a random variable, then the expectation of this function, right, will always be greater than if you compute the expectation of x and then apply the function on it. All right. So essentially, if you remember, what is expectation, right? So expectation is, you can compute expectation of any function, which will be equal to fx p of x dx for all x, right? So that's the expectation. So this value will always be greater than equal to if you compute x px dx, which is the expectation of x, and then apply the function on that. I'm sorry? Oh, right. Oh, yeah. So this function has to be convex by itself, right? So what should I just say somewhere? Fx is convex. All right. So in next class we'll see how to use this to come up with this graph that this graph, right? And then we'll come up with an algorithm which can now learn, sorry, this graph, right? And then we'll come up with an algorithm which can now quickly learn those two parameters. So in fact, if you're interested, you can look at the notebook, right? And in the notebook, I have sort of computed it. I've implemented the EM for one-dimensional case, and this is what you learn. So this approximates the real values very well, all right? But next time we are going to look at it. And then we are also going to look at how to do it for two-dimensional data as well. Any questions so far?